By considering the binomial expansion of 1 plus x to the power of 2m plus 1, prove that 2m plus 1 choose m is less than 2 to the power of 2m for any positive integer m. Okay, there is a second part to this question, but I think I'll just focus on the first one for now. Okay, so some sort of discrete looking math, combinatorics type thing. Off the top of my head, I don't really know how this is all going to come together. First thing I'm going to do is just write out the binomial expansion of this term. And then given that we're trying to prove some kind of inequality, I'm thinking maybe, you know, the first term, if we think of that as a function of x and do some kind of optimization, like a minimization or maximization or something like that, then maybe that's what will give rise to an inequality. Not really sure. Maybe there's a particular value of x we can substitute, which will give us something. Okay, so we're told to write out the binomial expansion of this, or to consider the binomial expansion of this. And we want to prove that 2m plus 1 choose m is less than 2 to the 2m for all positive integers m. Okay, so first let's try and remember the binomial expansion. So this is equal to a sum. K goes from 0 to 2m plus 1 of x, well, let's do the combinatorial part first. It'll be 2m plus 1 choose k times x to the k. So, you know, clearly there's something about the term corresponding to k equals m, perhaps. I'm tempted, I might even be tempted to take derivatives of this thing at some point. Right? Because if I call this f of x, then I know f of 0 is equal to 1. And I can compute derivatives somewhat easily. F prime of x is equal to 2m plus 1 times 1 plus x to the 2m. So f prime of 0 is equal to 2m plus 1. And f prime of 1 might also be important, or maybe just f of 1, because we're not looking for, you know, where am I going to get my power of 2 from? It looks like maybe by substituting x is equal to 1. So let's erase this for now. F of 0 is equal to 1, and f of 1 is equal to 2 to the power of 2m plus 1. So this is not exactly the thing we're looking to compute or compare, but okay. How about f prime? F prime of x is equal to 2m plus 1 times 1 plus x to the 2m. And I also have, if I take a derivative instead with the Taylor, or the binomial expansion, I also have that it's equal to the sum as k goes from 1 to 2m plus 1 of 2m plus 1 choose k times k x to the k minus 1. So I don't have, I mean, I could put a 0 there, but that term will end up just being 0. So how about I write down what is f prime of 0? F prime of 0 will be 2m plus 1 which we can also see that we get that this is true regardless of which of these two things we start with. Obviously, if I substitute x equals 0, this whole thing becomes 1. But you see it here as well. If I substitute x equals 0 here, then every single one of these terms becomes 0 except when k is equal to 1. And when k is equal to 1, this becomes 2m plus 1 choose 1, which is 2m plus 1. How about f prime of 1? So this will be 2m plus 1 times 2 to the 2m. So that comes from this. But it's also equal to the sum as k goes from 1 to 2m plus 1 of 2m plus 1 choose k times k. Does that have a nice formula of some sort? Let's write out 2m plus 1 choose k. That's equal to 2m plus 1 factorial divided by k factorial 2m plus 1 minus k factorial. And I'm seeing maybe some potential cancellations here. So if I now multiply by k, so that's just including that term, this is equal to 2m plus 1 factorial divided by k minus 1 factorial times 2m minus k minus 1. So I'm writing it like this because I'm seeing where some things might end up going. Okay. So now what I have, if I put everything together, I have 2m plus 1 times 2 to the 2m is equal to the sum, as k goes from 1 to 2m plus 1 of this thing. So all I've done is I'm just rewriting this equation and I'm replacing that with this thing. K minus 1 factorial 2m minus k minus 1 factorial. And so now I'm going to cancel a 2m plus 1 on both sides. So this numerator becomes 2m factorial divided by k minus 1 factorial 2m minus k minus 1 factorial. 2 to the 2m is equal to sum as k goes from 1 to 2m plus 1. This is 2m choose k minus 1. And if I allow instead k to go from 0 to 2m, I can just replace that with k. I haven't really proven anything here, though. I know this is an identity that is known. Oh, but that's fine. Yeah. This is a known identity, right? I mean, you can think of this in a few ways, but the you know, take the Pascal's triangle, and if you sum up across any one row, then you get a power of 2. That's what this is saying. You sum up all the terms in one row, you get a power of 2. But okay, maybe we go back to, maybe there's something we can do here. We can manipulate that. Yeah. Okay. So what is the maximum with respect to k of 2m choose k? This happens when k is equal to m. This is equal to 2m choose m. The maximum value of one of these combinatorial coefficients happens when the when the bottom number is half of the top number. Okay, so this shows that 2m choose k is less than or equal to 2m choose m. And it's a strict inequality except when k is equal to m. So this means 2 to the 2m. What I'm going to do here is I'm going to replace this with something bigger. Oh, no. Hold on a second. I wonder if I'm doing things kind of backwards, like, I mean, if I continue with my logic here, I'm going to get an inequality that I don't want. This is less than sum as k goes from 0 to 2m of 2m choose m, which is equal to the sum as k goes from, or no, this is equal to 2m choose m times the number of terms, which is 2m plus 1. So this gives me 2m plus 1 factorial divided by m factorial times 2 times m factorial. But that's not the inequality I want. What about, maybe I should just start with the, I'm going to do this all again without taking a derivative. I don't know why I was fixed on taking a derivative. So f of x is equal to 1 plus x to 2m plus 1, which is equal to the sum, k goes from 0 to 2m plus 1, of 2m plus 1. Choose k times x to the k. So if I just substitute x is equal to 1, I now have 2 to 2m plus 1 is equal to the sum, k goes from 0 to 2m plus 1, of 2m plus 1, choose k, and this is a, oh, but my inequality is going the wrong way again. I mean, one possible way of flipping this inequality is to let x equal -1. Or let the argument, let x equal, not -1, but like something negative, -3. Oh man. And I fear that I've gotten this method in my head and I won't be able to get it out or see a different way of doing this. Okay, so by considering the binomial expansion of 1 plus x to 2m plus 1, prove that 2m plus 1 choose m is less than 2 to 2m. Okay, so there's the binomial expansion. What happens if I take more derivatives? How many derivatives do I have to take for this thing to be identically 0? 2m plus 2? Wait, it's an odd power. It's an odd power, so it has no minimum or maximum. Wait a minute. Oh my goodness. Oh, for F's sake. Oh, for F's, wait. Let's go back to here. This means that 2 to the 2m is greater than any one of these terms. Could I get an expression like this except with 2m plus 1 here? I mean, you know, also for any k where this statement makes sense. So obviously, like in particular, it's true for 2m choose m, but we need it for 2m plus 1. Okay, let's go back to not the derivative, but the standard. 2 to the power of 2m plus 1 is equal to the sum, k goes from 0 to 2m plus 1 of 2m plus 1 choose k. Okay, I think I've got it here. So the key at this point is that 2m plus 1 choose m is equal to 2m plus 1 choose m plus 1. Right, let me just derive that. So 2m plus 1 choose m. This is 2m plus 1 factorial divided by m factorial m plus 1 factorial, which is the same as 2m plus 1 choose m plus 1. Okay, so we have that 2 to the 2m plus 1 is equal to, well, what I'm going to do is I'm going to say this is then greater than 2m plus 1 choose m plus 2m plus 1 choose m plus 1. So what I've done is I've taken two terms out of this sum, specifically when k is equal to m and when k is equal to m plus 1, and I've thrown out all the other ones. So of course I've made it smaller, but these two things are equal. This is greater, so these two things are the same, so it's just 2m plus 1 choose m times 2, so we'll cancel the 2. Yeah, so it was a lot more straightforward than I thought in the beginning. This should have taken a lot less time, but I just didn't see the way of doing this. You know, I saw this thing written in terms of x, and I was like, oh, let's treat this as a function and work in some calculus somehow. Obviously, not really necessary. Okay, there is a second part to this question, but I think what I'll do is I'll call this video an end, and I'll make a new video for the next part of this question. I haven't read the next part yet, but just a very brief glance at it makes it look a little bit more complicated. So it might even take longer than this. Thanks for the submission, and thanks for watching.